Hello guys, how's it going? We're just gonna check that everything here is streaming properly and that we're live. We're also going to check the audio from here. We're also going to check the audio, so it's good. And now let's come back to the introduction to embeddings with OpenAI API. Now we are going to do the third part. Yesterday we were working on the organizing the medical transcripts with OpenAI API, and then we started doing the embeddings, and we made like 2 lives. It was around 2 hours, and now we're gonna continue. I think this is a bit more advanced, so it's taking us longer to complete this course. But hopefully we'll finish that today. Maybe tomorrow, but hopefully today. And now we're gonna jump right into it, into the next chapter. I don't know, I already know it.
In this chapter, we'll begin to apply what you've already learned to implement the most popular embedding applications: semantic search, recommendation systems, and classification tasks. Let's start with semantic search. Recall that semantic search engines use embeddings to return the most semantically similar result to a search query. For example, a news website could enable semantic search by embedding news article information like the headline and topic. A user searching computer could then be returned a selection of computer-related headlines. There are 3 steps to semantic search: embed the search query and text to compare against, compute the cosine distances between the embedded search query and other embedded text, and finally, extract the text with the smallest cosine distance. Let's implement this semantic article search using the OpenAI API and Python. Here's the headlines data we'll be working with. We'll embed not only the headline text, but also the topic and keywords. To do this, we'll combine the information from each article into a single string that reflects the information stored in the dictionary, and the keywords are delimited with a comma and space. To combine these features for each article, we'll define a function called createArticleText. This function uses an f string, or formatted string, to return the desired string structure. F strings allow us to insert variables into strings without having to convert them into strings and concatenate them. F strings are created by specifying an f before the quotes, and note that we've defined a multi-line string using triple quotes. To insert an object, we use curly brackets and specify the variable or other Python code to insert. For the article headline and topic, these values are extracted using their keys and inserted into the string at the desired locations. The keywords are a little trickier because they were stored as a list rather than a string. To convert the keywords list into a string, we use the joinList method, which joins the content of the list together into a single string. The method is called on the string we want to delimit each keyword with, in this case, a comma and space. Calling the function on the final headline shows the text in the desired formatted string. To apply the function and combine the features for each article, we use a list comprehension, calling our function on each article in articles. Finally, to embed these strings, we call the createEmbeddings function on the result. Recall that this creates a list of embeddings for each input using the OpenAI API. Now that we have our embeddings, it's time to compute cosine distances. We'll define a function called findNClosest that takes a query vector, the embedded search query, and embeddings to compare against, our embedded articles, and return the n most similar results based on their cosine distances. For each embedding, we calculate the cosine distance to the query vector and store it in a dictionary.
So you get the embeddings, you enumerate them, and you get the index of the embedding. You get the distance of cosine of the query vector and the embedding. And in the distances, you append the distance and the index. All right.
Along with the embeddings index, which we append to a list called distances. To sort the distances list by the distance key in each dictionary, we
sorted distances, the key lambda.
use the sorted function and its key argument. The key argument takes a function to evaluate each dictionary in distances and sort by. In this case, it's a lambda function that accesses the distance key from each dictionary. Finally, the function returns the closest n results. Time to bring all the semantic search pieces together. We'll query our embeddings using the text AI. First, we embed the search query using our createEmbeddings function and extract its embeddings by 0 indexing. Next, we use the findNClosest function to find the 3 closest hits based on our article embeddings. Finally, to extract the most similar headlines, we loop through each hit using the hits index to subset the corresponding headline and print. As we'd expect, the top results specifically mention AI, and the others are on similar topics. Now it's your turn.
Okay. Okay, define a function to combine the relevant features into a single string. When you embed product information, you are limited to only embedding the product source description, which captures some but not all of the relevant product information. In this exercise, you will embed title, short description, category, and features to capture much more information. So I need to here call create product text of product for product in. Here's already defined products, and then here in the title we should put product, and this is going to be title. Then here is going to be short description. Then here is going to be category, and here is going to be, so here's going to be something like this, comma, and that join, and then in here I'm going to put the product, and here I got the features. And then product embeddings is gonna be the it's going to be the all the create embeddings, but so it should be create embeddings, and I should pass here the product test text. If I run, should be alright. Okay, and if I submit, it should be good too. Yes, good. But let's now write it into our code. So let's close out of this, and let's minimize it, and here maximizing. So the create embeddings, we already have it. In this case, we don't need this. We are going to, here we're also going to run cloud because we need to expand the samples. Here we need to copy and paste this. Here, and then create embeddings, reproduce text, and now what we need to do is like cooperative fat. I think we're really running low on RAM, so now in the afternoon, after finishing this course, we will need to go into a deep cleaning before making the project. So I guess that tomorrow we're gonna do the project. Today we're just gonna try to finish, make video reels, and tomorrow we make the project, okay? Because it's taking it's taking it longer to run this, and I need to go faster. So I'm gonna copy for this project, for this file. can you create sample products? Oh, here looks something like this. Max 5 elements. Then yeah. And this is gonna create a list of embeddings for each product. And then when I run on git bash, I will be able to let's not submit, and let's go to the next exercise. Okay, now sorting by similarity. Now that you have embedded all of your features, the next step is to compute the similarities. Yeah, I'm good here. Okay, in this you will define a function find n closest, which computes the cosine distances between a query vector and a list of embeddings and return the n smallest under indexes. So I'm gonna, okay, this is something important from SciPy Spatial. So here I should put distance dot cosine, and here it should be the query vector and the embedding. So the distance is going to be the dist, and the index is going to be like this. Then the distance is sorted is going to be sorted, and this is going to get the distances, and it's gonna do a lambda of x, and this is gonna get something like the distance, and it's gonna sort by this property, and then this is sorted from 0 to 3, from till 3. So I'm gonna run the code. It should be it. Let's submit it. By distance in the key. What is wrong in here? Okay, let me check, because I think that there is something wrong in here in this lambda, but sorted gets key. So the key that I should use, it's equals to lambda x and x distance. And it's hard coded also, so I should be from the beginning till end. Yeah, and this should run good. Yeah, this is good too. So here we should do the same in the 8, but this is gonna be called find and closest. This is gonna be basically the same code, but we are also gonna define this, and this distance cosine is gonna be from here, from distance, and then when yeah, well, I guess that in the next one I will find. Okay, because I didn't do anything on Sunday. Uh, so just in case, I'm gonna put here the find the n closest, and then in this exercise I'm gonna already use the find n closest to actually compute the closest one. So the query vector is gonna be the create embeddings, and I'm gonna pass here the query text, and I'm just gonna get the first element. Then the hits is gonna be the find and closest of this one with the with the and the prog embeddings. All right. So here I should get the hit, and in previously we had the index, so it should be index, and I will get the product, and that should be it. Prog is not defined. How come it was here? Okay, let me reload the page. Yeah, and this is the closest one that it found. So in order to do this here, we're gonna rename 8 9, because otherwise it wouldn't be self-enclosed. I'm gonna do this. I have here already no, it's not here. So the program values are here. Then here I got the create embeddings of the query. So I have the query vector of the product embeddings from here. Then I get the hits, and I get the closest one. So now if I run the 8 9, oh sorry, I need to go to the embeddings. So Python 8 9. Now we should find the 5 closest procs to the computer query text with embeddings. So let's see how it rolls. Yeah, I have 1 2. I think it wouldn't compile, and you know what? Because there is only 4 elements here. So you know what we're gonna do? We're just gonna do, instead of 5, we're gonna do just product embeddings, and I'm gonna put here 2. And so I just get like the 2 closest one, because there is only 4 elements in that list. Let's submit the answer here. Did you miss the argument? That's what I thought. And here I need to find the 5 closest. So this is gonna be 5. Submit. Continue. Now we're gonna go to our recommendation systems. So here, as you saw, in my case I just put 2, so that's why I got 2. Okay, so it's good, it's saved, and let's continue with the next lecture.
Welcome back. In this video, we'll discuss another common application of embeddings, recommendation systems. Recommendation systems work almost exactly the same as semantic search engines. We have a group of items that we potentially want to recommend, and at least one data point that we want to recommend based on. We embed the potential recommendations and the data point we have, calculate the cosine distances, and recommend the item or items that are closest in the vector space. This similarity in approach means that a lot of the code is exactly the same. Let's take a look. We're returning to the news article dataset to design a recommendation system that recommends the 3 most similar articles to the one currently being read. This recommendation will be based on the article's headline, topic, and keywords stored in a dictionary called current article. This particular article is about the impact of computer hardware on AI advancement. To prepare both of these objects for embedding, we'll first need to combine the features into a single string for each article. We'll be reusing the createArticleText function you may remember from earlier, which extracts the headline, topic, and keywords and uses an F string to combine them into a single string. To combine the features, we call the function on each article in articles using a list comprehension and do the same for the current article. By printing, you can see that the function correctly formatted the current article's information. Next, we embed both sets of article strings using the createEmbeddings function from function.
Let's concentrate a bit. Create article, return article text, find the correlation.
Correctly formatted the current article's information. Next, we embed both sets of article strings using the createEmbeddings function from earlier, which allows us to create requests to the OpenAI embedding model in a more repeatable way. Finally, to compute the cosine distances and extract the nearest distances, we'll use our find n closest function, which computes the cosine distances, sorts them, and returns the n smallest and their index. We'll call this function on both sets of embedded articles and then loop through the results, returning the headline of each article in the 3 most similar articles.
So far it's just basically the same code, but the same code, but now we're embedding an article instead of products.
There we have it. This is a good start, but a more sophisticated system would use not only the current article to base the recommendations on, but also the other articles in the user's history. Let's consider that a user has visited 2 articles stored in user history. How can we provide recommendations based on multiple data points? This is the situation we have, where the user has seen 2 articles embedded in blue, and we want to recommend the most similar articles. Articles they haven't seen yet are shown in red. To find the most similar vector to 2 vectors, we'll combine the 2 vectors into one by taking the mean. Then, we'll compute cosine distances as we did before and recommend the closest vector. If the nearest point has already been viewed, we'll make sure to return the nearest unseen article. The first 2 steps to embed the user history are the same as before, combining the features for each article and embedding the resulting strings. The only difference is that we take the mean to aggregate the 2 vectors into one that we can
Mean history embeddings. So here we are creating the mean of the history embeddings, and then we're computing that into one.
compare with the other articles.
All right.
For the articles to recommend, we filter the list so it only contains articles not in the user history. Then, as before, we combine the features and embed the text. Finally, we compute the cosine distances using the same find n closest function, only this time passing it the mean of the embedded user history. Then, we subset the filtered article list to find the most similar articles. Here they are.
So basically it's the same, but now we do the mean history embeddings.
Notice that the article headlined Tech Giant buys 49% stake in AI startup wasn't recommended, as the user had already seen it. Now it's your turn.
All right, that's good. In this, your recommendation for an online retailer that sells a variety of products. Have been provided with a list of dictionaries of products available on the site. And the dictionary for the last product the user visited stored in last product. Okay, let's finish this and let's take a break, okay? Because we're on live 21 minutes, 25. All right. Recommendation system for an online retailer that sells a variety of products. The system recommends 3 similar products to users who visited a product page but don't purchase. Based on the last page they visited, you have been provided with a list of dictionaries of products available on the site. The features for the last product. So it looks like this. The last product text. So here I should put the final clauses, and here is gonna be the 3 smallest distance, and here I should do the last product embeddings. So in this create product text, I'm creating basically, so I have already this stuff. So the product text should be this one. Create product text for product in products. So here's the product text, and then the create embeddings is going to receive the product text, and the last product embeddings is going to be the same, but for the last product only. And then this create embeddings is gonna receive the last product text, and I'm gonna get the 0 element, and this is just gonna be a recommendation for one product. So this is gonna be so this is gonna be called pro recommendation. Rename is gonna be 10 product recommendation, and here I have the products. Here I find the final closest, the create product text, and then we're gonna do we're gonna do this. All right. then we're gonna go here. Then after this, we create the last product. So, but now we need the. Wait, let me submit this first. Yeah, and now I'm gonna do this. Please on this file. Complete it by creating last product variable, because we need that. The products are already there. Then by create embeddings and create product list is already there too. Now we just need the now we just need to get the create this last product one so we can. Yeah, that's correct. Yes. Yeah, so if I do this one, and the last product in this case is going to be, so I have a smartphone, I have luxury diamond, RC. Our last product is wireless noise canceling headphones. So I'm assuming that the closest one should be, it must be the smartphone. So I'm gonna do the 10. Yeah, yeah, it just makes sense. And I mean, and I think both of the previous answers looked kind of similar, but because of the fact that the search was computed, and in this case, the recommendation of, so we're going quite closely to the same semantic meaning, right? So that's why we're getting something similar. Adding user history to the recommendation engine. So this, for many recommendation cases, such as film or purchase recommendation based, you can embed all of some user history or more accurate relevant information. Okay. For so here I'm getting the history text. The history embeddings will be create embeddings of this history text, and then the mean history mp mean, and it's gonna do this. And it was something like axis 0. And then the filter products to remove any user history. Product filter should be products that filter product and product article is equals to. Okay, I'm gonna put some JavaScript here so to check how does it transform into Python. Product article equals fixture that has product. Let's run it like this and see what it does. And the prog text is gonna be the same as here, but it's gonna be here progs filtered products. So for product, create product text, product embeddings. So this is gonna be the same here, create embeddings. Then here I'm gonna pass the product texts. And then the mean history embeddings with the product embeddings that doesn't contain, because I just filter here. I'm just gonna, what is wrong on this code? And it's gonna make me the fix here probably because of the filter function. So I should do, there is no filter, so I should do an array like this. So product for product in products where what? If product not in user history. Okay, it's valid. Now let's submit this. That's good. Now we're going to do the 11. This is, what is this called? Recommendation with user history. And here recommendation is with double M. So here I should copy all of this, but in this case I don't need the last product. Now I will need to ask Cloud, please expand this code, adding the user history. Yeah, so I'm gonna check the history of articles that the person has seen as a variable here, because that's the missing one there. And then we're gonna run it. You know, just to make sure, because we have now 2 articles that are about, yes, now we have 2 articles that are about glowing skin, and the other one is luxury diamond necklace. So let's make the, yes, and make the history more about beauty items. So I, instead of doing the and add more beauty items to the products. Because now what I'm trying to do is I'm trying to guide it in a way so I get the recommendation of beauty products. Yeah, so now if I run the Python 11 should recommend the two other beauty products, but that are the two other beauty products, but that are not in the history. So probably it's gonna recommend this one and this one. Let's see. Let's update it and let's see what it returns. So far here is good already. Okay. And now this task was complete. And now let's run this here. Yeah, and it now recommended this beauty products, so it's good. Well, that's pretty good so far. Now we're gonna go to the gym, and we're gonna walk the dog a bit, and then we're gonna come back in the afternoon with finishing this second chapter. And let's keep rolling into it. So thank you very much, guys. It was a pleasure as always.